Okay, folks, so we're going to dive deeper into some of this homework in Chapter 1, just in case you're struggling with some of these problems. I'm not going to do all, but I'm going to show you an example of how to systematically think about and solve some of the problems assigned in homework for Chapter 1. Let's go ahead and get started. So, I'm going to jump straight into problem 5. As I said, I'm not going to do the easier ones, but I'm going to do ones that I want you to maybe think about. So this one's a little bit tricky. Hypothesis, theory, and law. So a hypothesis, remember, is a untested explanation, but it can eventually be tested. The theory is usually very well tested at this point and does some explanation. And a law is just a stated observation. Just after many explanations, scientists, after many experiments, explain conservation of mass by stating that matter is composed of atoms. I think that might fit under theory. Many experiments. An explanation that has been tested and verified. Ooh, that might go under theory, it might go under hypothesis. I could be wrong. Description that predicts what happens but not explain how. That is perfect for a law. No explanation. Observation. Entomologist surmises but has not verified why gray moths survive best on gray tree trunks. That sounds perfect for a hypothesis. Untested explanation. So, now a hypothesis can be tested and it doesn't immediately lead to theory. So, but usually a hypothesis starts there. Now, this is 6 is the scientific method. So, how do we usually start? You usually start by, we can look back to the slide, but make observation. And then you would form an initial hypothesis. You would test the initial hypothesis. Now, if testing discredits the initial hypothesis, we will have to revise the hypothesis. Wait, where did it go? If testing, then we'll test our new hypothesis. If, after it confirms, this can eventually become a theory. I know exactly what happened. When be careful when you put them in, that they don't jump out of order. Form initial hypothesis. Okay, there we go. So note, I made an error. So I only get 98 out of 100 points. That's fine. I'm going to skip ahead to problem number 9. Problem number 9 is going to be some type of significant digits of a measured results. If you have a liquid, you're measuring the bottom of the bubble. Since we're measuring a distance, we're measuring from eraser to tip. Now, the rule of measuring a thing is that you always go one decimal place past the most accurate line. So the accurate line here for the pencil is decimeter. So we have 1 decimeter, 2 decimeters. So this is between 1 and 2 decimeters. Where it's at, it's hard to figure out approximately. I'm going to guesstimate. This is my estimation place. It's a third of the way there. So I'm going to say 1.3. I cannot estimate more than that because there is no more line. Now, in this one, same pencil, we now have markings every 1/10 of a decimeter. And this looks like it's between 1.2 and 1.3, closer to the 1.3. So I can say maybe this is 1.28. I can estimate that additional place because there's more markings. So you always go one space past the initial marking. Now, maybe you said 1.2 for that first answer. You could have, that would have probably been a accepted answer. So there's some type of like leeway when it comes to your answers, like 5% off, as long as you're doing it to the proper number of decimal places. So I just want to make sure you understood the estimation there. How do we do the estimation? Now I'm going to skip straight to 15. So looking at this is a Sig Figs easy math problem, but I have to do it in order of operation. So I'm going to go to the document camera for this, so you can see it worked out. Okay, so with this in mind, let's adjust that. The first step is to do this simple subtraction. So I'm going to set this up 6.5 minus 6.31. This is an unknown sig fig, so we cannot keep that. Your calculator should come up with 0.19. 0.19. However, we can only round this to 0.2. So this is going to be my first value is 0.2. So I have one sig fig remaining. 0.2 divided by 3.59. So when we add and subtract, we keep the position of the lower number of sig figs. So this is a lower position, so we can only keep to the tenths place. Now when we divide or multiply, we keep the sheer number of sig figs. So 1 sig fig divided by 3 sig figs, your calculator comes up as 0.0557. I'm rounding there just to leave out 3 sig figs, and so I have to round it to 1. So I have to round to 0.06. 0.06. That's where I'm at. Let's see. Point. Divided by. Okay, I know they should have accepted this, but 0.05. Okay, the problem I had, I'm going to go back to that. What happened? They should have accepted it, but since it was such a small number, there was not enough leeway. But because I rounded here and rounded again, it changed my number from 0.0529 to 0.557. So it rounded up instead of rounded down. So what I had to do was 0.19, knowing I can only keep those digits, divided by 3.59. And that made it really kind of annoying. So they'll be. That's why I'm doing this. Sometimes that may happen. Make sure it's not a rounding error. Going from 0.06 to 0.05 is greater than a 5% change. Here's some dimensional analysis for number 20. Steve races to the nearest taco stand at lunchtime, sees his pedometer record his speed at 109.9 centimeters a second. And he wants to say, what is this in kilometers per hour? This in kilometers per hour. So we're going to have to go centimeters to meters to kilometers, and seconds to minutes to hours. So I'm setting this up. 109.9 centimeters in 1 second. That's my starting point. So I'm going to start by converting this. The dimensional analysis. So I set that up. There is 100 centimeters in 1 meter. There is 1,000 meters in 1 kilometer. Set that up. Centimeters cancel centimeters. Meters cancel meters. And I'm left with kilometers per second. Now there are 60 seconds in 1 minute and 60 minutes in 1 hour. Minutes cancel minutes, seconds cancel seconds. We are left with kilometers in an hour. Once we've set this up, it is a mere matter of multiplication and division. So everything on top gets multiplied. 109.9 times 60 times 60. We're going to divide by everything on bottom. Divided by 100. Divide by 1,000. We get the whole number is 3.9564. If we're rounding to sig figs, definition. This guy with 4 sig figs controls 4 sig figs. So 3.956 is what I should report. Now it doesn't ask for that. So if I reported one more digit, it shouldn't mark it off. So unless it physically asks you for significant figures, you're okay if you go too far. It would have probably accepted one less as well. So looking at, I'm going to do 21 and 22 while we're at it. 21. Mercury, also known as quicksilver, metallic element and liquid at room temperature. Mercury's density is found to be 4. What's its density? If its mass is 459.0 grams, and its volume is 34.43 milliliters. Note the density is in grams per milliliter, not grams per not kilograms per liter, grams per milliliter. So that tells us what we got to do. If I'm watching my units, that's telling me exactly what I got to do. Density is mass over volume. But the units itself tell me exactly what I need. 459.0 grams divided by 34.43 milliliters. Grams over milliliters gives me the correct units. So 459 divided by 34.43. 4 sig figs, I keep 4 sig figs. So I'm going to round there, even though the calculator keeps going. 13.33. As long as my number is within 5% of 13.33, it will be correct. And the last one. Convert 184 Fahrenheit, 84.1 Fahrenheit to Kelvin. I'm going to do this guy as well. It's pretty straightforward. The hardest part is remembering the equations. So from Fahrenheit, the Fahrenheit equation is minus 32 times 5/9 equals Celsius. Minus 32 in parentheses times 5/9 equals Celsius. And then Celsius plus 273.15 equals Kelvin. But essentially plus 273. Actually, no, it's... Yeah, that's right. So, first step is to convert Fahrenheit to Celsius. 184.1 minus 32 times 5 divided by 9. 4.1 times... Gotta do it in the correct order. Times 5 divided by... I could divide by 9 and times 5, but it's not boiling point. It's not boiling point. It's hot. It's hot. But it's not at boiling point. What's the boiling point of water? 212 Fahrenheit. What's the boiling point of water in Celsius? 100 degrees. So it's not above boiling. 152. That should be a good check. 273. If I had done that in the wrong order, you would have got 273.6. Ooh, it's above boiling. If I did 184.1 plus 32, yeah, you would have. Even if you had done the 5/9, it's above boiling. 84.1 times 5/9. Yeah, if you'd done the minus in the wrong order, one way to check whether you know it's done in the right order, the freezing point of water in Fahrenheit is 32. The freezing point of water in Celsius is 0. Now, if you take 32 and times 5/9 and then minus 32, you're not going to get 0. 32 minus 32 is 0. 0 times any number is 0. So that's the only real way to get 0 to 0. So that tells me that. So now that I have the 84.5, I'm going to add my 273.15. That gets me 357.65, which is going to be 357.7. But so the hardest part is turning Fahrenheit to Celsius. But doing those two things should not be too much of a challenge. I just wanted to show you some of those math problems. Still leave plenty of math problems for you yourself to do. And even though I showed you those problems, you will have slightly different problems. The work I've shown you should still more or less be valid. This problem 22 is still going to be turning Celsius, or like Fahrenheit to Kelvin, or Kelvin to Fahrenheit. Those equations I just gave you are still valid. It's just a matter of, hey, can I apply the work for my numbers and not Dr. Evans's numbers? But with that in mind, have a good day.